Okay, so here we are at 2:40, and welcome to all of you that have hung in with us all day. This is the fourth session, our last two presentations before we finish up today. I'm Tom McDermott. I'm the moderator for this session. Please remember to enter questions in the Q&A as you go along here. For our first talk, I would like to introduce Justin Valenti. He's a PhD candidate in aerospace engineering at Penn State. As a Walker graduate assistant, his primary research interests are in UAV design and additive manufacturing. And his talk is rapid aerostructural design of UAV wings for direct toolpath generation. Justin, over to you.
Thank you very much, Tom. Full disclosure up front, I would not consider this a systems engineering project. It's an aerospace engineering project. But I work with a lot of systems engineers, so we decided it would be an interesting talk to put this in sort of a systems engineering lens. So the main goal of my research is to develop a streamlined tool chain to design and fabricate wings with additive manufacturing. To do that, we sort of chunked it out into three overarching problems. We need to design the outer shape of the wing, and that's really an aerodynamic design problem. We needed to design the internal structure of the wing, which is really a structural problem. And then we needed to take that design and somehow give it to the 3D printer, which is an additive manufacturing process design problem. So to do this, I had to kind of take a holistic view and take all of these things together and come up with a way to get a nice clean product at the end of it. Looking at some 3D printed additively manufactured wings of the past, I picked out four that are sort of typify what I look at. The first one in the upper left is the Sulsa, and that was the first, at least in literature, the first additively manufactured UAV. This was done with SLS out of the UK. Moving down, the Navy Scout was really interesting. The Navy took an open source UAV from Thingiverse and sort of adapted it to their purposes. It was really cool. On the upper right, we have the 3D printed Mustang from 3D Lab Prints, and you can buy these plans online for $20 and print a scale Mustang all for yourself, which I've done. And then right in the middle is a picture of me standing next to ARL's 3D printed airplane, which is actually how I got into the group that I'm currently at. And that project was actually partially funded by SERC. So it all full circle. It's why I'm here now. Some overarching themes. We see airplanes that are roughly 1 to 2 meters in wingspan, all printed out of plastic. So that's where the focus of my work is. Interesting from a design for additive manufacturing standpoint. There are all these restrictions and all these opportunities that are given to you, sort of dropped on your lap when you decide to 3D print a UAV. And when the restrictions, when it comes to a restriction, you have to sort of abide by all of the restrictions when you're thinking of 3D printing anything. And the opportunities that are afforded, you kind of got to work hard to really reap the benefits of those opportunities. A lot of times people like to say free complexity from 3D printing, and there is a lot of ways that 3D printing provides a lot more practical complexity to you, but there's a lot of design work that has to go in to really capture that. So some things on the restriction side that I'm really need to focus on is making sure that any sort of rib or internal structure doesn't require any support structure from 3D printing, because it'll be difficult to get that out from the internals of the wing. Making sure my skin doesn't warp. I typically like to have thin walls on my wing, so ABS tends to warp way too much. Typically PLA is where you got to be. Material anisotropy. A lot of times you print the wing to have good curves, but at the expense of the structural properties of the wing. Layer lines that come from 3D printing are often of a scale that will affect the boundary layer. all the things you got to take into account. From the opportunity standpoint, the things that I'm going to focus on is taking advantage of the complexity given to me by 3D printing, consolidating my parts, taking that internal structure, printing it with the external structure, which is a little bit different than how you normally make a wing, and making my wing mission specific, designing a process that's easy enough to iterate on, that every time I have a new mission, I can just pop out a new wing for. So putting this into sort of a systems engineering lens, we have mission requirements, aerodynamic design, structural design, and then fabrication, and then having to validate and verify that process all the way back up. And for my work, I'm really going to focus on the sort of the lower end of the left side of the V. So how do I design my wing aerodynamically? How do I come up with a structural design? And how do I fabricate that? From an aerodynamic standpoint, there is a brand new theory that came out 100 years ago called lifting line theory. And we've been putting, my advisor and I have been sort of massaging the mathematics to come up with real easy and quick ways to generate wing designs from this. And what do I mean by a wing design? I mean, when you look at a wing, you have a chord distribution, which is from the top at any given location along the span, the wingspan. You have what's the distance from the leading to the trailing edge of that wing. So that's the chord distribution. The twist distribution is how is that wing twisted as you go from the root to the span. A lot of the times wings won't just be linearly extruded. There will be some twist to it. So we want to figure out what's the chord and the twist of our wing. And typically we want that to create some sort of lift distribution, the distribution of lift as you go across the span. So how can we tailor the geometry to give the desired aerodynamics? And what we've done is sort of come up with two overarching ways that you can design your wing. You can either design your wing for a single angle of attack or a single flight condition, whether that be cruise or whether that be a climb out or something. And from the equation, the sort of the basic lifting line equations, it's pretty easy to pull out lift, chord, and twist. And any two of those distributions uniquely defines the third. So if you want a super easy rectangular wing that gives you a specific lift distribution, then you can quickly back out what the twist would be to give you that distribution. And similarly, for if you want a lift distribution and twist distribution, you can know what the chord distribution will give. That will give you that. A more interesting thing that we've been coming up with and publishing on lately is how to take a wing and how to design it to operate at two different angles of attack or flight conditions. So maybe a cruise and a climb out, and use either a lift distribution or a lift coefficient distribution, which is more of a 2D angle of 2D aerodynamic thing. And how to use those aerodynamic distributions at two different angles of attack and come out with the chord and the twist simultaneously, which has been fun. But this has given us an opportunity to, if we know what aerodynamics we want, how to quickly come up with outer wing geometry and get our aerodynamic design. Moving forward to structural design, if we know what our outer wing should look like, we need to figure out a way to design the internal structure such that the wing can withstand those flight loads. Lifting line theory collapses the wing to a single line running in the spanwise direction. So it sort of follows, to match that simplicity, to use beam bending theory, where you again collapse the wing to a single line running in the spanwise direction, but use classical beam bending theory to come up with what sort of structure you need. So if the forces on the wing, across the wing, are the lift distribution, which I've already spoken about, but you also have the wing weight itself that will sort of give a negative load. And then you have any external loads, maybe any sort of pods or something that you might want to hang from the wings, or any motors or anything. So you sum up all the loads across the wing, and you can come up with a bending moment distribution. And from that bending moment distribution, right at the very bottom, we can use beam bending theory to come up with a required moment of inertia for the wing across the span. Once we do that, we can come up with ways to quickly design structure to give you that required moment of inertia. So if we want to carry the loads primarily through the skin, we've come up with simplified expressions to give you the moment of inertia of skin. If you want to carry it through a rectangular spar, then you can use the spar geometry you tailor the spar width to give you a desired moment of inertia. Or in an additive manufacturing sense, if you want to have a lattice infill or some sort of a foam going on, you can have the void fraction or the volume fraction, of the lattice itself that you can use to tailor the moment of inertia across the span. And the nice thing about beam bending theory is it's linear. So if you want any combination, you can combine those two and add, sum up to your desired moment of inertia to give you your needed structure. Moving forward to the sorts of the family of structures that I'm most interested in is this thing called curvilinear spars. And it shows up in the Mustang that I showed earlier, where they have this, it's like a 2D lattice structure from the top, and it gives a really clean, really strong structure. And this sort of structure has been analyzed in a much higher fidelity sense using higher order finite element and designed using topology optimization to come up with these sorts of families of structures. I want to hit that at a much lower fidelity level to give us much faster means to design my wing. So peeking back at the beam bending math I already showed, at any given point along the span, if you chop your wing, you get, looking at the curvilinear spars, you get a few different spars spread out in the chordwise direction that will contribute to your bending structure. So a typical airfoil is thick in the middle and gets thinner out towards the front and the back. So you can tailor the location of these spars to tailor the beam bending properties of the spar itself. So if I need a lot of bending inertia, I will scrunch a couple spars right at the max thickness point of my airfoil. But as the requirement for bending moment relaxes out towards the wingtips, I can move those spars forward and aft to match my bending inertia requirements. So using that, I can quickly come up with a method to generate my internal structure. Now, combining these into a single aerostructural design, I have my aerodynamics design, which gives me my outer wing shape, and I have my structural design, which gives me my internal wing structure. I can iterate between those two, where I give the outer shape to my wing structure designer and I give my wing weight to the dynamic designer and converge on a solution. And what I converge on in the end is really not a CAD model at all. It's just a couple vectors defining my twist and my chord, and maybe a matrix defining where my spar locations are going to be. So I really haven't come up with a 3D model at this point, just a low order representation of that. Now, if I were to take this and try to 3D print it, I would probably need to come up with a way to get that into CAD, and then I would need to slice it in the slicer of my choice and give it to my 3D printer. But if I don't know my whole process up front, I could run into many pitfalls as I give that file, as I move my design along through the various steps. So lack of upfront knowledge can really, it can lead to an unprintable part. If I don't know, if my CAD and slicers don't talk well to each other, I can come up with a CAD model that my slicer doesn't understand. So you really need to take this whole process as one process and design it as one thing. So what I've done is I've realized that once I have my aerostructural design, I really don't need to go to CAD at all. If I do some clever coding, the first time I ever represent my geometry can be in the form of my G code or the instructions for my 3D printer. So direct toolpath generation, or as I'm calling it, is coming up with your design using whatever design math you choose, and then outputting that directly as your instructions to your 3D printer or additive manufacturing machine. And that's currently a lot of the focus of what I'm doing at the moment. The real beauty that this, in conclusion, the beauty that all this provides is if you know what problem you're going to solve, and you're going to solve that a bunch of times, like maybe you have a mission specific UAV that you want the wings to change based on what you're going to fly. If you automate the lower portion of the V cycle, then you don't have to worry about designing wings every time. You can worry about what that mission is going to be, and you have a nice clean tool to give you wings that you know are going to work every time. So with that, I think I am 30 seconds under, and I'll call it a win at that. So I'll give it back to Tom.
Thank you, Justin. Actually, a few minutes early. So I sent out a comment. I thought this was a great example of a system engineering approach to derive some first order principles to develop a new set of design tools. That was excellent in the space. So I don't know if you said, Justin, if you've actually ever taken this all the way through to printing an airplane yet.
I have not. No. Short answer is no. I'm slowly getting all of the chunks together. So most of the aerodynamics is already done. I'm still working on exactly the structural the method that I use to get that structure. And I've gotten parts of that done, and I'm starting to get the actual G-code generator, and I have bits and pieces of that done, but I've yet to get it all the way. And hopefully at that point, people will have to call me a doctor.
Yeah, you'll be done. So we've got actually 3 questions that came up. Joe Bradley, can this be applied to other platforms like ship hull forms or submarines?
Sorry, Tom, I think I missed what you said. Can you repeat that?
Did you hear me, Justin?
No, I didn't. Can you please repeat that?
Yeah, Joe Bradley asked, can this be applied to other platforms like...
Oh, can this be applied to other... Are you looking at, can this be applied to other ships or hulls?
Yeah.
Yeah, I think it can. You would just need to, if you understand what the design aspects are, and I'm sure there are plenty of theories that have been developed to design boat hulls. I see no reason why you can't come up with a similar, at this point, a fluid dynamic design tool and a structural design tool, and simply represent that and give that to a 3D printer. But you would need to redesign the process.
You're getting a number of questions. Stephanie Chiesi, have you investigated the use of design structure matrices for evaluating and optimizing the workflow?
I've not.
Probably some good advice.
Yeah.
What are the possible downsides of direct toolpath generation? Do you think the CAD model is completely unnecessary? That's an interesting question.
I've already been posed this, and I think the CAD model from a visualization standpoint is really important. So in my final process that I presented, the CAD model is optional, and I would probably add highly recommended. It's not a key point in the process, but wondering how the wing interacts with the rest of the airplane, it's probably good that you have a CAD model representation at the end. The nice thing about this is it doesn't go through the CAD model, so there's not geometric error that might be introduced when the slicer with a CAD program triangulates your design, and then the slicer slices up that triangulation. So I think the CAD model is still recommended, It's just no longer in the path to the printer.
Hey, thank you. So I believe that's all the questions. I want to thank you, Justin, for a really interesting presentation.